So in this video, we are going to make use of the moment generating function approach to compute the average symbol error probability under the fading environment for linear modulations. So let's have a recap of what is the moment generating function. So moment generating function is defined as m gamma of s, where s is some complex number, is defined as integral from 0 to infinity, the PDF of your fading distribution, the gamma of gamma, times e to the power s gamma, the gamma. And you can see that it is very similar to the Laplace transform of the PDF of the fading distribution. In fact, a Laplace transform of P gamma of gamma is nothing but the moment generating function of minus s. So that's the relation between the Laplace transform and the moment generating function of a PDF of a fading distribution. So we, in the previous videos, we said that the moment generating function approach can be very useful in computing the average symbol error probability. And we said that, for instance, if we talk about DPSK, differential phase shift keying, the probability of the bit error for differential phase shift keying in an EWGN environment is 1/2 e to the power minus gamma b. So you see that's a very simple exponential function for which you have the error probability in an EWGN environment. And now if you want to compute what would be the average symbol error probability for a DPSK under fading, what you have to do is, so your PB bar, that is your average bit error probability, would be integral from 0 to infinity, your PDF under EWGN, we call it 1/2 e to the power minus gamma, times P gamma of gamma, D gamma. And you can right away see that this average bit error probability for a DPSK is very similar to the moment generating functions formula. So you can see that this is nothing but 1/2 m gamma of minus 1. So that is what it is, right? So this is the moment generating function where s is replaced by minus 1. So that is as simple as that. So this is your average symbol error probability for DPSK under fading environment. The important thing is that this is a generic formula. That is, all you need to do is to change the moment generating function for a specific fading distribution, and you would get a average symbol error probability for that particular fading distribution. For instance, if we talk about the Rayleigh fading, so for Rayleigh fading, your moment generating function m gamma of s for Rayleigh fading your m gamma of s is nothing but 1/1 minus s times gamma s bar. So that is what it is for Rayleigh fading. So that means if you want to compute what is m gamma of minus 1, say for Rayleigh fading, so that would be equals to 1/1. If you replace this s by minus 1, that would be plus gamma s bar, right? And now you can very easily see what would be the average symbol error probability for DPSK under Rayleigh fading. So your PB bar for Rayleigh fading your average bit error probability would be equals to 1/2 times 1/1 plus gamma s bar. So that is your average bit error probability for DPSK, and we have made use of the moment generating function approach. So that was for DPSK, and now we would move on from DPSK to to the to other linear modulation schemes. And for that, we said that we need to make use of what is called the alternate Q function representation, because you would have a Q function rather than an exponential for a EWGN error probability equation. And that's why we need an alternate Q function representation. The alternate Q function representation was proposed by Craig in 1993. And what did it do? So let's recall what is our Q function. So our Q function, Q of Z, is nothing but the integral of the tail of a standard normal Gaussian, standard normal random variable. That means it is integral from Z to infinity, 1 over root 2 pi, e to the power minus some dummy variable squared by 2 dt, where t is your dummy variable here. So there are two things which would change in the alternate representation. One is that this argument would no more be in the limit, and the second, this infinite integral would change to a finite integral. So then in the alternate form, your Q of Z can be represented as 1 over pi integral from 0 to pi by 2 e to the power minus z square over 2 sine square phi d phi, where z must be greater than 0. So this is your Q function representation, which is an alternate form of the Q function representation. So you can see that both of that changes which I mentioned have been uh, have been done here. So the first thing is the argument is no more in the limits of the Q function, and the second is that the infinite integral has been changed to a finite integral of some trigonometric function. So that is very good. Not only we have this alternate Q function representation, we can also have an alternate Q square function representation as well. And that would be used if we want to compute the average symbol error probability of QAM, quadrature amplitude modulation. So in which you would have Q of Z multiplied by Q of Z, that would give you a Q square of Z. So if you have Q square of Z, your alternate representation is very similar. The only thing that changes is that the limit would be integral would be from 0 to pi by 4 instead of 0 to pi by 2. The rest of the things do not change. And z should be greater than 0. So this is the alternate Q square representation for the so that it can be used for linear modulation schemes. So now let's try to represent how any if we want to compute the average symbol error probability of a linear modulation scheme, how would you go about it? So let's try to do an example. For example, if we have this BPSK, we know that for BPSK, your bit error probability in AWGN is nothing but Q function of root 2 gamma B. So what would be this PB using the alternate Q function representation? So your PB in an AWGN channel, right, in AWGN would be equals to 1 over pi integral from 0 to pi by 2 e to the power minus z square would be minus 2 gamma over 2 sine squared phi d phi. This 2 would cancel out with this 2. So um, this is your error probability, bit error probability in an AWGN channel for BPSK. More generally, for any generic linear modulation, for linear modulations, we said that your symbol error probability, PS, in an AWGN channel can be written as alpha m Q function of root beta m gamma s. So that is your generic formula that can be used for any linear modulation scheme, and depending upon what linear modulation scheme you're talking about, this alpha m and beta m would change. They would also depend upon what approximation are you using, whether or not you are using the nearest neighbor approximation and all that. So let's try to represent this in terms of the Q function and try to find out what is average symbol error probability here. So our PS, as we said, is nothing but alpha m Q function of beta m gamma s under the root. So we would be changing these constants alpha m and beta m slightly here. So we would say that this alpha m is nothing but alpha. So we'll call it alpha in this representation. And we would say that we would define another parameter g, that g would be equals to beta m by 2. Yeah. This g would be equals to beta m by 2. Exactly. So in other words, your symbol error probability in AWGN can be rewritten as alpha Q function of root. So if g is equals to beta m by 2, then beta m would be equals to 2g. It would be 2g gamma s. So that is the same function. We have done some change of variables. And now if you want to represent this using the alternate Q function representation, that would be equals to alpha over pi, because there was 1 over pi in the alternate form, integral from 0 to pi by 2, finite integral e to the power minus z squared would be minus 2g gamma s, if you want, over 2 sine squared phi d phi. These two cancel out with this 2. So probably that was the reason the author has chosen this g in such a manner, so that this 2 in the denominator of the Q function cancels out with this 2. So you have this. So this is your symbol error probability in AWGN channel. Now, if you want to compute what is the average symbol error probability, if you want to compute PS bar, then we know that PS bar would be integral from 0 to infinity, your PS as a function of gamma, right? P gamma of gamma d gamma. So if we apply this here, so your average symbol error probability would be equals to alpha over pi integral from 0 to pi by 2 So now you have to integrate this. So you have an integral from 0 to infinity, and then you would plug in this e to the power minus g gamma s over sine square phi d phi times p gamma of gamma d gamma. So what we have done is that we have plugged in the value of this PS of gamma, which is nothing but this integral here. This is nothing but the PS of gamma, and you're integrating, including this alpha over pi, right? So this is your PS of gamma, and you're integrating this PS of gamma over the fading distribution. So you can see how can we go about this. We can do the change of the order of this integration, and that would lead us to the moment generating function. So your PS bar can be written as alpha over pi integral from 0 to pi by 2 integral from 0 to infinity e to the power minus g gamma s over sine squared phi e gamma of gamma d gamma, right, times d phi. So now you can see that this expression, the inner integral, can be written in terms of the moment generating function. So this inner integral, you can try to guess what moment generating function it is. This integral is nothing but m gamma s of, and s is replaced by minus g over sine squared phi. That means that your PS bar, the final expression for the PS bar, is nothing but alpha over pi, a finite integral from 0 to pi by 2 of what? Of the moment generating function, where moment generating function of what? Of minus g over sine squared phi d phi, right? And now again, you can make use of your moment generating function, and you have, for different distributions, you have different moment generating function. For Rayleigh fading, you know that your m gamma of s is nothing but 1 over 1 minus s gamma s bar. But now instead of s, you need to put what? You need to put minus g over sine squared phi. Your m gamma of minus g over sine squared phi would be equals to 1 over 1 plus g over sine squared phi times gamma s bar. Or you can also write it as 1 plus g over sine squared phi gamma s bar whole inverse. One of the same thing. So this is your moment generating function for the Rayleigh fading. And hence you can plug in this moment generating function of minus gamma, m gamma of minus g over sine squared phi for a particular fading distribution. And you can compute what is the average symbol error probability. So if you want to write me the exact expression, that would be equals to PS bar is equals to alpha over pi integral from 0 to pi by 2, a finite integral of what? Of 1 plus g over sine squared phi times gamma s bar whole inverse d phi. So this integral can be solved using the tables and or the numerical approaches to compute these integrals can be solved easily. So this has given you the average symbol error probability for any type of fading. So the power of the moment generating function is that it allows you to compute the average symbol error probability for any particular type of fading. All you need to do is to change this moment generating function for that particular fading distribution, and you would get the average symbol error probability for that particular fading distribution, right? So in this equation, this is a very generic one. This can be used for any particular type of fading distribution for which you can compute the moment generating function. So now let's go ahead and try to compute the average symbol error probability for the quadrature amplitude modulation. Uh, so let's do that. For quadrature amplitude modulation, if you recall, the expression for the symbol error probability in an AWGN channel was not a very simple one. So let me write that expression. Let me copy that. So the expression for the symbol error probability for quadrature amplitude modulation was, the PS is nothing but 1 minus the probability of correct detection, and we said that the probability of the correct detection would be 1 minus the branch error probability whole squared, and the branch error probability was 2 times so remember, mind you, we are talking about square constellation here, so that we have a capital M, which would be a non-decimal number, or under root of M, sorry. Under root of M would be a non-decimal number. We are talking about square constellations over root M, Q function of root 3 gamma S bar over M minus 1 whole square. So this is your symbol error probability for a quadrature amplitude modulation in an AWGN channel. Right? So you can see that it's not a very simple equation, but we would be able to compute the average symbol error probability using the moment generating function approach, even for quadrature amplitude modulation, and that would be an exact expression, because this is an exact expression for the symbol error probability in AWGN. So your PS can be written as, you can rewrite it as 1 minus, and now if you open the squares, it would be equals to 1 plus the square would be 4 times 1 minus 1 over root M whole squared, Q squared of root 3 gamma S bar over M minus 1. And this would continue. So this is 1 plus 1 squared plus this term squared, and we would have minus 2 times the first term, which is 1, and then the second term, it would be 2 times 1 minus 1 over root M. You can see that we are representing this term as 1 minus 1 over root M, Q function of root 3 gamma S bar over M minus 1. So that is your symbol error probability in an AWGN channel. And now we would apply the alternate Q function approach. So you can see that we have a Q squared, but we have an alternate representation for the Q squared as well. Let's try to compute this expression. Okay, so we have this expression for the symbol error probability in AWGN. So if you want to write this expression in terms of the alternate Q function representation, your symbol error probability would be equals to, this one would cancel out once you open these brackets, and there would be a minus sign with this term and plus sign with this term. So I would write this term first and this term afterwards. You would have the first term I'm writing is would be this, so minus times this function would be 4 times 1 minus 1 over root M. And now the Q function of this term would be integral. So Q function in the alternate form would have a term of 1 over pi. So let me put 1 over pi here. Integral from 0 to pi by 2 e to the power let me write it as minus g over sine square phi. And I will let you know what is g in a moment. Rather, you can guess that, right? Already. Minus g over sine square phi d phi. Where you know that in the alternate Q function representation, you have minus 2 over minus z over 2 sine square phi, where this all of this is your z, right? So your g would be, so g would be 1 by 2 times this function 3 over m minus 1. So your g would be 1.5 over m minus 1. So you can see it right away, but I would write it as well. So this is only the first term. Minus the second term would be 4 over pi, because we would be representing this q square in terms of the alternate representation, times 1 minus 1 over root m whole squared, integral from 0 to pi by 4 e to the power minus g over sine squared phi d phi, where your g is nothing but 1.5 over m minus 1. This is what your g is, right? So in the alternate form, you can write it like this. So this is your symbol error probability in AWGN, not in the form of for the average symbol error probability. But moving from here to the average symbol error probability is very straightforward. So your symbol error probability on average for any type of weighting distribution would be equals to integral from 0 to infinity your ps of gamma, p gamma of gamma, d gamma, right? And now, because we need to integrate this from 0 to infinity, and as we did in the upper expression here, so once we plugged in the formula for the Q function, then we did what? We changed the order of the integration. So let me write it in that form already, because that would be redundant here. So let me write in the form where you can already represent these functions as a moment generating function. So your symbol error probability would be your symbol error probability in AWGN averaged over the fading distribution. So that would be equals to 4 over pi times 1 minus 1 over root m, these are the constants, integral from 0 to pi by 2, integral from 0 to infinity, e to the power minus g over sine squared phi d phi, minus 4 over pi times 1 minus 1 over root m whole squared, integral from 0 to pi by 4, integral from 0 to infinity, e to the power minus g over sine squared phi d phi. Of course, this would be our gamma here. Gamma, so sorry about that. So that there must be a gamma here. So now you can see that your average symbol error probability can be represented as a moment generating function. So this is nothing but moment generating function where your s is replaced by minus g over sine squared phi. Similarly, this is a moment generating function where your s is replaced by minus g over sine squared phi, and hence your average symbol error probability for quadrature amplitude modulation. Let me write it with black. Is average simple error probability is 4 over pi 1 minus 1 over root m, a finite integral from 0 to pi by 2 of what? Of the moment generating function m gamma s of minus g over sine squared phi d phi minus 4 over pi 1 minus 1 over root m whole squared, a finite integral, this time from 0 to pi by 4 of what? Of your moment generating function m gamma s of minus g over sine square phi d phi. This is what is your average simple error probability for a quadrature amplitude modulation, and that too for any type of distribution. So for fading for Rayleigh distribution, you would replace your moment generating function by 1 over 1 minus s gamma s bar, right? So we know that already. And for Nakagami M fading, you would have a different moment generating function, right? So in short, moment generating function is a very powerful approach. It allows you to compute the average simple error probability for linear modulation schemes, for differential phase shift keying, and that too for any type of fading distribution. We'll stop the recording here and we'll come back in the next video.